And our last presentation of the symposium will be by Simona Vegetti, returning back to astrophysics. Simona is, I guess, the most senior of the Pappalardo Fellows presenting at this symposium. And so she'll be, as she gets set up, preparing to tell us about her work related to the structure and formation of galaxies.
Trying to put in the wrong hole. It's not picking up. It might be going now. Well, okay. Thanks for sticking all the way to the end. What I'm going to talk about is one of my favorite subjects in astrophysics, because it's the one I'm working on. So this is about looking for tiny galaxies in the distant universe. First of all, I'd like to thank Neil and Jane, and because I'm Italian, and because Neil effectively is Italian, I'm going to do it in Italian, and I wish I knew it in Sicilian, but I don't. So, grazie mille for the opportunities. So, the way the astronomers think about the universe can be simply summarized by a pie chart where you have that 33% of the universe is made of dark energy, which is a form of energy we don't know much about, except that it's driving an accelerated expansion of the universe. The 23% of mass is in what we call dark matter, and even in this case, we don't know very much, except that it's weakly interacting with the rest of kind of matter, which is only 4% of the universe, and this is basically what we can probe directly, so stars and gas and dust, and supernova, galaxies, whatever. So the universe, by a matter point of view, is essentially dominated by dark matter. And this is quite convenient in a sense, because dark matter is essentially only gravity, and gravity, in a way, it's easy. And based on this pie chart, we now have a model for the formation of structures in the universe, which is basically driven by dark matter. This is the standard cosmological model. And what I'm going to show you in a second is basically a numerical simulation where people simulate the formation of a galaxy from the early universe till nowadays, but they're only looking in dark matter because that's easy to simulate. So you're going to see colors. Those colors should be interpreted as density. So the brighter the color, the higher the density. So we start with a universe which is homogeneous and uniform. So you see not much, but you should be able to see soon tiny density fluctuations that slowly grow in time. And these tiny density fluctuations, at a certain point, they're big enough that they create objects. They are able to separate from the expansion of the universe and give rise to gravitationally bound objects that we call dark matter halos. And the first halos that form are the smallest one. And then these small halos will merge together to form bigger and bigger halos. So it's a hierarchical scenario, where, as you can see here, tiny objects merge along filaments and sort of get together. And at the end, they will form a bigger halo in the center. And the interesting thing is that while merging, many of these objects will be destroyed, and so their particles will be part of this larger halo. But a lot of these tiny halos will survive around the main halo as satellites. So objects gravitationally bound to the main halo. So one of the predictions of this model is the existence of thousands of satellites around your main object. And so this is basically how our own galaxy would look like in dark matter glasses. In reality, the way it looks like depends on the property of dark matter. So if you have cold dark matter glasses, this is how the Milky Way would look like. So you have thousands of satellites. If you have a warm dark matter, then this is how the Milky Way would look like. So you can see there are far less satellites. Here you have streams, which are basically these objects that come in and they are tidally disrupted. And at the end, you basically end up with a much smoother distribution. And so counting the number of satellites is a way to probe the properties of dark matter. I can use this. The problem is that this is how we think galaxies are, but this is what we see. These are the galaxies that we see. So you have massive elliptical galaxies, mostly made by old stars, no gas, so they're not forming stars anymore, very little dust. Here you have galaxies more like our own Milky Way, forming stars rich of gas and rich of dust. And so the question is, how do you go from here to the picture I showed you before, or the other way around? And so matching observation and simulation is what is keeping awake plenty of astronomers. And the business becomes pretty tricky when instead of looking at the galaxies, you look at their satellites. So as I showed you in the picture before, in simulation you have thousands, 10,000s of satellites per galaxy. But if you take a telescope and start counting the satellites around the Milky Way, you only have at most 30. And so the question is, where are the missing satellites? And a way to see this problem is by counting the satellites and measuring their mass. And so you can construct what we call a mass function. So you count as many objects as you have for a certain mass. And this is what numerical simulations are predicting. So they're telling us there should be plenty of dark matter satellites around the Milky Way. But this is what we measure. So there are only few luminous satellites around the Milky Way. And of course, there are plenty of solutions. One thing you could say is that these are dark, these are luminous. So the missing ones are those that do not form stars. And a way to prevent star formation is, for example, is to invoke supernovae, because as Laura was saying, supernovae release a lot of energy. And so if you have a tiny galaxy and suddenly a supernova goes off, they blow away all the gas, and suddenly you won't be able to form stars anymore. Another solution is that the theory is wrong, so we might have to rethink our standard cosmological model. Or another third possibility is that the Milky Way is actually a special system and is not telling us much about what the other galaxies are doing. So the question becomes, how do you find satellites in other galaxies? It's already a tricky business finding galaxies in our own galaxies. This is how one of these satellites look like. So it's just a bare overdensity of stars. So it's already a challenge to find these in the Milky Way, and many of them may not contain stars. So how do you find something that does not emit light in a faraway galaxy? And the way to do it is to use gravitational lensing. What is gravitational lensing? Well, suppose you're on Earth with your telescope, and you're looking at a faraway galaxy. And suppose that between you and the source galaxy, there's another galaxy. Then the mass of the lens galaxy will deflect the light rays coming from the background, and you will form multiple images. And by studying the structure of these multiple images, you can actually infer the mass distribution of this galaxy and also detect satellites. And before I show you how, let me give you a trick that you can try tonight at dinner if you really want to understand what gravitational lensing is. You take a candle, that's your source galaxy, and you take a glass wine, those with the stem, and you look at the candle through the stem, and as you can see, you form multiple distorted images of the same candle. And this is exactly how lensing works. And in fact, if you look at the candle exactly through the stem, you form what we call an Einstein ring. Okay, so this is exactly the same trick. So if you now take the candle again, and you replace it with a blue star-forming galaxy, you take the stem and you replace it with a red massive elliptical galaxy, what you get are images like this. And by studying these images, you know the mass properties of this object. Now, suppose you have a satellite orbiting around this galaxy. What would be its effect? Well, you can see it here. This is a group of galaxies, and you have a tiny satellite belonging to the major galaxy. And as you can see, the satellite is perturbing your Einstein ring. So suddenly you have a break, and it forms a tiny Einstein ring. And the cool thing is that this perturbation will be formed even if this satellite here was not containing light. So you might not see the satellite, but you might see its effect. And by using basically this signature, we can basically go and detect satellites even when they're purely made of dark matter, and even if they're far away in the universe. Just to prove you that the method works, suppose you take this system, and suppose for a second that you don't know that there's a luminous satellite there, and you try to apply our technique to reconstruct the original data. And as you can see, because you're not including this satellite, your model, your best model, is actually very poor, and it looks very different from your original data. And you can see it here. This is basically the difference between the model and the data. And this is how your candle behind would look like, as you would infer from these images. So if you don't include the little guy, you're poorly reconstructing your features. Now, the way we detect galaxy satellites is basically by assuming that the main galaxy can be described as a smooth distribution of mass, and then the satellites are spikes of density on top of this smooth. So if in your model you allow for the presence of spikes, then suddenly you can detect the corresponding satellite. And so if you take, again, this system, and you pretend you don't know, again, that there's a satellite, and suddenly you allow for density spikes, you can suddenly fit the data. And this is, the difference between the two is actually much smaller than you had before. This is, again, the reconstructed background galaxy. And as you can see here, there's a positive density correction right in the position where the satellite is. Okay? So in this case, it was easy because we knew. But it also works in cases in which the perturbation is not that strong, and you actually don't know whether there's a satellite or not. So now that we have a technique, we need a sample. And we have two samples. The first one comes from the Sloan ACS survey, which was created here at MIT by Scott Barles. And it gave us 100 red galaxies lensing blue star-forming galaxies at higher redshift. And we'd start looking at this sample by looking at this interesting object, which is called the Jackpot. Because in this case, this is a very rare case in which not only you have a candle and a glass, but you have a glass, a candle, and then another candle, and the second candle will create a second ring. And this is pretty rare. And so if you apply our game to this object, what you find is that there's another satellite. There's basically a satellite in this position, which corresponds to this position here. And so you can see there's no obvious signature at the moment. But when you allow to, basically when you apply this gravitational imaging technique, you're able to find a satellite. And you also find that it has a mass of 10 to the 9 solar masses. So now this satellite is quite big, because this regime is not exactly where simulations and observation are diverging. And so ideally, you'd like to push this number down, at least by an order of magnitude. And it turns out that the Hubble Space Telescope is actually not the best telescope to do it. But what is actually much better is ground-based observations with the Keck telescope, who has an adaptive optic system. So the mirror adapts to correct for the atmospheric perturbations. And so this is a 4 lens systems. These are observed with HSD. And these are the same system observed from the ground at Hawaii with Keck. And as you can see, the image quality is much better. And because the image quality is much better, if here you can detect 10 to the 9 satellites, here you can push it down of an order of magnitude. So suddenly, you're able to detect Milky Way kind of satellites. So the same satellites that we see in the Milky Way, now we're able to detect them at a much farther distance. And so we look at this, we start looking at this system here. And as you can see here, we found another satellite, which this time is much smaller. It's 10 to the 8 solar masses. Again, this is the same structure. This is the original data. This is how the model looks like. This is the difference between the model and the data. This is the reconstructed background source. And here, you have a positive density correction. And we actually looked also at the HSD data, which is a much poorer quality data. And this density correction is there even in that case. So we are confident it's a true detection. So what these two detections tell us about our cosmological model? Well, as I showed you before, these are the predictions from the theory, and these are the observations. So this curve goes as to the -2, power to the -2, and this goes like, it's flatter, so has like a slope of -1. And if we take our detection together, we find that the probability for this slope is actually peaked around -1. And so in this regime here, we're actually more consistent with observation than we are consistent with simulation. And of course, these are only two systems. We're now in the process of analyzing the 100 SLAX lenses. But if these results were confirmed, then we might have to rethink the way we think galaxy forms. And so I go to my conclusion. I hope I convinced you that detecting satellites in faraway galaxies is important because it allows you to set constraints on the properties of dark matter in a way that can be done anywhere in any other way. From the ground. Okay. From the ground, we can actually do better than with the Hubble Space Telescopes if you have adaptive optics system. And using this technique, we actually been able to detect very tiny objects very far away in the universe in a way that was not possible before. And these observations are actually telling us there might be something tricky with the theory of galaxy formation, and that maybe the properties of dark matter are not as cold as we think. And I leave it there. Thanks.
Wow. Questions, please. Neil.
Your observations so far indicate almost one or two, at the most one or two satellites, and yet your original premise of depending on whether it was warm or cold dark matter implied lots of different satellites.
Yeah, but you can.
And
The fact that you don't detect, it's an information. The fact that you don't detect many other, it's an information. The fact that you don't see them, and if you know how to quantify your sensitivity, it's an information that you can use to constrain this slope. So the fact that so if you say, I'm sensitive to a certain mass, and you don't see that mass, you can use that information to constrain. But this is, the way this is challenging the theory is actually more complicated than that. Because we do see a certain number. The problem is how they're distributed in mass. And the second problem is where they're located, because they are very close, both in projection and likely in 3D. They are very close to the center of the galaxy. And that's very hard in simulation to get a satellite so close to the center. And so there is more mass in satellites in observation than in simulation, which reverses the problem a little bit. So it's a bit more complicated than just 2 or 3.
It's another puzzle. Krishna first.
I think related to Neil's question, how is the sensitivity of your method, how does it depend on how far away the satellite is from the center?
Well, we only see where...
How far out could you find it?
Well, it depends. So because we're looking at galaxies, you would only see within the innermost 5-10 kiloparsecs, so quite close to the center, because that's where the ring is formed. If suddenly your lens is not a galaxy, but it's a cluster of galaxies, then your ring would be much larger. And at that point, you would detect them further away. So in principle, there's no restriction to the method. It's just which kind of mass the main lens has, essentially.
Bob.
Will James Webb Telescope be significantly better than Hubble for these studies?
I don't know. It would need follow-up imaging anyway, I think. I think you could get initial images, but then you would have to probably follow them up again. I don't know. Yeah. I know that, for example, future radio telescope could give us a lot of lenses, and that would be like the SKA kind of thing, or Euclid will give us a lot of lenses that we can apply the method to.
Webb will not have the same kind of resolution as HST,
Yeah.
the wavelengths it's working. So for the Keck imaging, this is really a tour de force. I haven't seen those images before.
Yeah,
And
it's pretty impressive.
how are those the only 4 which have been done? And,
No.
and what other kinds of systems have had such high resolution imaging?
So my collaborators are right now at Keck observing, and we are hoping to have at least a sample of 10, 15 more objects to look at. Wow. And we actually decided to go for, so the objects I presented here, it's like a elliptical galaxy lensing a star-forming galaxy. We decided to go from elliptical because they are much brighter, and so in 5 minutes you get these kind of images instead of 3 hours. So it's getting quite interesting, yeah. Because at that point we might be able to push the mass of halos that we see to 10 to the 7 rather than 10 to the 8, and that's really where it's a test of cosmology.
Great. Claude?
When you get down to the lower mass range of the satellites, how important is it to include some baryonic physics in actually deriving the mass function, or is it still?
So for the way we derive the mass function, it's essentially a statistical argument where you basically calculate what is the chance that if I have a certain slope, I get this observable. So the baryonic physics.
Well, I meant in the model.
In the simulations.
Yeah, in the simulation, that's the other big question. I mean, the problem of astrophysics now is we have not a great handle on the physics of gas. And so, as I was saying before, a way to keep those dark is to invoke supernova feedback or other procedure. But people are trying and are working on it, but we don't have cosmological numerical simulation that simulates a galaxy from beginning to the end with gas, because A, it's computationally very expensive, and B, we only understand gas physics to a certain resolution, so it's very hard to simulate. So there's a lot of effects which are hidden in the simulation that we don't have a handle of.
Are there other questions? Then let us thank Simona for a wonderful presentation.